So, what I'd like to do is take you through how to find an equation to model a linear relationship from all of the different representations that we look at in math. So, from words, from a table of values, and from a graph. So, remembering that in general, if we want to model a linear relationship using algebraically using an equation, in general, we know that the y, which is the dependent variable, is equal to the rate of change times x, which is the independent variable, plus the initial value. So if we can remember this general formula, and if we can pick off what is the dependent variable, the rate of change, the independent variable, and the initial value, then we can always come up with an equation to model a linear relationship. So going back to a pizza example, and this is our example of how to do it from words. So we've got the cost of a pizza is $8 for a basic cheese pizza, plus an additional 50 cents per topping. So when we look at this, we can pick off the key information. So first of all, we know that $8 is the basic pizza. So that's going to be my initial value of $8. And then I see additional 50 cents per topping. And whenever I see the word per, I know I'm talking about a rate of change. So I've got the rate of change is equal to $0.5 per topping, so 50 cents per topping. So there's our initial value and there's our rate of change. And then we want to look to see what the variables are. So I know I'm looking at two things. I'm looking at, and if I look here kind of at the rate of change always tells us what our variables are. So at the top here, I have a dollar sign. So that's going to represent cost. And on the bottom, I have my number of toppings. So dollars per topping. So that's going to be our, that's going to actually give us our hint as to what the variables are. So remembering that when we do rates of change, we always have the rise in the top and we have the run on the bottom. So rate of change is rise over run. And I know that rise are my y's and that runs are my x's. So my y's, or my dependent variables, are going to be connected to the cost. So my y is going to be cost in dollars. And to shorten that down, I'm just going to call that C. On the bottom, I have my run. I know run means I'm going back and forth. So that's my x's. And my x's is my independent variable. So the number of toppings is on the bottom of my rate of change. So that's going to be my independent variable. And I'm just going to call that n for number of toppings. So I have two variables. My independent variable is the number of toppings, or n. The dependent variable is the cost in dollars, or C. The initial value is $8. The rate of change is 50 cents per topping. So when I go back to my original equation, y equals the rate of change x plus the initial value, well, now I know that the dependent variable is the cost, is equal to the rate of change, which is 50 cents per topping. So I'm going to put in my number of toppings for my independent variable, and then I've got my initial value of $8. So the cost is equal to 0.5n plus 8. And now you can use this equation to figure out the cost of a number of different numbers of toppings of pizzas. So there's our algebraic model. Okay, we can do the same thing from a table of values. So here I have a table of values, and so when I label a table of values, remember that you always put your x column first and your y column second. In other words, we always put our independent variable column first and our dependent variable column second. So my independent variable, my x, is going to be the number of raffle tickets. So x is my number of raffle tickets, and I'm just going to call that n for number. And then y is the total cost of raffle tickets in dollars. So I know that y is the total cost, and I'm just going to call that C to shorten that down into a single variable. So I've got my independent variable is n, my dependent variable is the total cost, which is C. Okay. Next, I'm going to look for my initial value. Now, in this table of values, originally, if you look, it starts at 2, and then it goes 2, 4, 8, 10. And then it goes 1, 2, 4, 5. So actually, I'm going to look at my rate of change first. So I'm going to calculate my rate of change. Anytime I find the rate of change from my table of values, I always write down my formula first. Rate of change is equal to rise over run. So I know that in the table of values that my rise are connected to my y's because my y's go up and down. So I go from 1 to 2, I go up 1. To go from 2 to 4, I go up 2. To go 4 to 5, I go up 1. And I know that my runs are my x's because they run across this way horizontally. So I go from 2 to 4, I go up 2. From 4 to 8, I go up 4. From 8 to 10, I go up 2. So what I can do is I can pick any matching rise and run to figure out my rate of change. So when I did this here, I chose my first one here. So I had the rise of run and the run of 2. So I've got rise of a run is 1 over 2, which is 0.5. And that should be, if I put units on there, I should have dollars per ticket, so 50 cents per ticket. But I wanted to note too that if I look at a different spot, so say if I look here I'm going up 2 for a run of 4. And 2 divided by 4 is also 0.5. So as long as it's a linear relationship, as this is, it doesn't matter which rise and run we pick, we should still get the same rate of change. So I get my rate of change to be 0.5 or 50 cents per ticket. And then I want to look back to see my initial value. And if you look at this table of values, the initial value, we always want to start at 0. So how much would it be for 0 tickets? And that's not on here. So what I'm going to do is I'm going to extrapolate that information. I'm going to go backwards. So I'm going to go back from 2 to 0, and I just kind of add in my own value here. So if I go back 2 here, I saw on this side that every time I go back 2 from my run, I'm going to go back 1 on my rise. So that gives me a new value in my table of values, 0, 0, just by following that pattern in the opposite direction. So I can see that my initial value, when my independent variable is equal to 0, my dependent variable is my initial value, which is 0 as well. So now again, I have my variables. So I know that independent variable is n, dependent variable is c, initial value is 0, rate of change is 0.5. I'm going to go back to my original equation, y equals the rate of change x plus the initial value, and I'm just going to put in my values. So I know my dependent variable is cost is equal to my rate of change of 0.5. My independent variable is n, the number of tickets, and I know that my initial value is 0. So I get cost is equal to 50 cents per ticket, or 0.5 n plus 0, or simply c is equal to 0.5 n. Okay, so now what I can do is I can use this formula to find the cost of different amounts of tickets, and I can test it out. So for example, let's say I can test this point out here. If I have 10 tickets, that means that the cost is going to be equal to 0.5 times 10, which is 5. And sure enough, if I look in my table of values, I get 5 to be my cost. I could try it for the 8. So if I know that the number of tickets is 8, I'm going to take my cost is going to be equal to 0.5 times 8, which is 4. And again, I have 4 as my cost in my table of values. So I can check to see if my equation matches up with the table of values and the numbers that I should get from those calculations. Okay, so again, we picked off independent variable, dependent variable, initial value, rate of change, and then we were able to put it into our formula to come up with a nice, clean, linear equation to model the situation. Okay, and finally, exact same thing, only this time we're going to do it from a graph. Again, I want to be able to pick off what my independent variable is, my dependent variable, initial value, and rate of change. I'm going to start off with the variables here. So I know that my independent variable is always my x, so that's going to be on my x-axis. And when I look at my x-axis here, I have time and hours. So my independent variable is going to be time and hours, and I'm just going to call that h to simplify it up. And my dependent variable is always on my y-axis. In this case, it's distance. So I've got distance in kilometers, and I'm just going to call that d. So instead of calling it y, I'm going to replace it with something that connects it to what we're actually modeling, which is distance. So I'll call it d. So I've got my two variables. Now I want to pick off my initial value. So on our graph for initial value, I always look to see what is the where does the line hit the y-axis, and in this case it starts at 0. So I've got my initial value is equal to 0, or 0 kilometers. And then finally, I want to calculate my rate of change. anytime I'm calculating rate of change for my graph, I always write out my formula. So I've got rate of change is equal to rise over run. And then using my scale, I'm going to pick 2 clean points on this line, and it shouldn't matter where I pick those 2 points. You should always get the same rate of change because it's constant. So here, I picked this point here, which is the point 1 and 80. And then the second point I picked here was 3 and 240. So you can see I always draw my rate triangle on here just to help me keep track of what the numbers are. So if I start at 80 and I go up to 240, my rise is going to be 160 kilometers. And if I start at 1 and I run over to 3, my run is going to be 2 hours. So my rise over run is going to be 160 kilometers in 2 hours. And I always want to put my rate of change into lowest terms or as a unit rate. So 160 divided by 2 is 80, so I have 80 kilometers per hour. Okay, so now I've got everything I need. So again, I'm going to start off with my formula, y equals the rate of change x plus the initial value. Y, my dependent variable, is going to be distance, so d. My rate of change is 80 kilometers per hour, so I put in my 80. My independent variable is time, which I called h for hours, and my initial value is going to be 0. So I get 8d equals 80h plus 0, or simply the distance is equal to 80 times the number of hours, so 80h. And again, you can check it out. So if I was looking here at 5, I had 5 hours. Well, 80 times 5 is 400. And sure enough, if I look here after 5 hours, it has gone 400 kilometers. So you can always check to see if your equation matches up with your graph. Okay. And finally, there's one more thing I just wanted to point out to you, some new terminology. And that is the idea of something called partial variation versus direct variation. So these 2 examples right here, these are examples of direct variation. They're direct variation because they are both linear relationships, so they're constant rates of change. And the initial value for both of these examples is 0. So anytime you have a linear relationship that has a constant rate of change and initial value of 0, that's called direct variation. And I always remember it goes directly through 0, so it's direct variation. This one here has an initial value of 8. It's not 0. So anytime you have a linear relationship that has a constant rate of change but doesn't have an initial value of 0, we call that partial variation. So this is partial variation because it's linear and has an initial value that's not equal to 0. And these 2 are called direct variation because they're linear and they have initial values that are equal to 0. Okay? So there we go. Anytime we want to find a rate of change, an algebraic relationship to model a line, if we can figure out what the dependent variable is, the rate of change, the independent variable, and the initial value is, we can always come up with our algebraic model for the equation.